Is it clear that energy should be conserved?
Yeah.
So what's happening is that we're trading off some gravitational potential energy and converting it into kinetic energy. So if we pick the reference height for gravitational potential energy to be the initial height of the masses, what's the initial energy? Zero. It's not moving, and neither of them has gravitational potential energy. So we're trying to find angular velocity. Let's work on the change in potential first. What's the potential energy in the final configuration? So M1 went down. So I'm going to start actually with M2. M2 went up a distance h. M1 went down a distance h. And what about the pulley? No change. Okay, it just rotated around, but its center of mass didn't move. Okay, so that would be, I think, the final potential energy. What about the final kinetic energy? So I have three things that are moving. I have 1/2 m1. Now, is there a difference between v1 and v2? Or can I just get away with calling both of them v if I'm only worrying about the magnitude? If the string doesn't stretch, then however much, I was trying to indicate this with the red arrows, however much M2 goes up, then the pulley rotates an analogous amount, which we'll get to, and M1 goes down. So these three lengths have to be the same. So I'm going to call this v squared, 1/2 m2 v squared. And what about for the pulley? So it should be up there, right? We have 1/2 I omega squared. Do we know what the moment of inertia of the pulley is? We're going to assume it's a uniform disk, so that works out to be what? 1/2 mp r squared. And this would be great, except that I have both v and omega, and I need to tie those together to simplify. So what's the relationship between v, omega, and r? So if mass 1 is moving down at speed v, then the pulley must be rotating at omega such that v is equal to omega times r. Okay. Then I can substitute. I'm aiming for who? I'm aiming for omega. Is that what I'm trying to find? What is angular velocity? Yeah, so I want to get rid of v in favor of omega. So I will rewrite the kinetic energy here as 1/2 m1 plus m2 times omega squared r squared plus 1/2 mp r squared times omega squared. Aha, so 1/4 would be better. Thank you. So now if I equate initial energy with final energy, I get 0 is equal to m2 minus m1 gh plus 1/2 m1 plus m2 plus half mp r squared omega squared. So separating, we're going to have 1/2 sum of the masses omega squared r squared is equal to, I'm going to reverse the order, m1 minus m2 gh, and now divide through, and I get omega squared is equal to m1 minus m2 gh with a 2 that comes up from here, divided by m1 plus m2 plus 1/2 mp, and r squared. And now, with a little bit of eraser physics, I have omega, which I think is on the slide. Ha! Okay? So that, I would argue, is easier than having to go through, figure out the torques, solve for everything internal, figure out the angular acceleration, and integrate in order to get angular velocity, and then integrate again to get angular position so we know when it falls a distance h, what time it took, and then plug the time in order to get the angular velocity. Agreed? Energy makes life easier. So if you only care about the endpoints and you're not too worried about the time that it takes, energy is going to be your friend.